There are visuals now related to the planet Mercury, again from our solar system program. And there are a couple of things here I would like to point out. In fact, things which need to be improved from what we have. Although when we are showing this in the dome, we don't have these issues which I am talking about. If you look at this video, there is a place where Mercury double sunrise is described, and for some reason it could not quite be created from our own dome software. We're still working on trying to do that. So it was imported from one video about Mercury double sunrise from public domain, and so since this was a small video, it was kept on one side of the dome visual. So there is this Mercury sunrise going back. The background of it merges into black. So whenever you have a small video where the background is merging into black and you put it in the rest of your sky software, things work all right. And particularly in our system where we have very high contrast ratio, so it's possible to you keep small video in one part of the dome where it merges into black and then put it in the background of the stars. At one point, however, you can see the frame where the sun rises and then the globe. I mean it's just touching, and there is this square frame which can be seen, though it can't be seen in our dome when we show it to the public because of our dome brightness and contrast ratio issues. However, there is this. And then there is a part where we are talking about precession of perihelion of Mercury. And here these animations were created one after other, movement of Mercury combined in semi-transparent mode, so that you have one orbit of Mercury, then another, the small precession can then be viewed in this. So this small piece is related to Mercury, from its views to spacecraft views to what if we land on Mercury, what is it we are going to see, to back again viewing it from the Earth and precession of perihelion of Mercury. What you are going to be viewing now are recordings from computer monitor taken at the planetarium. So these are nowhere near the original. You will be losing the viewing the resolution both in the video as well as the sound, but they are used here just to give an idea about matching content to narration.
Traveling to the planets is much more difficult due to the vast distances of the planets. To get an idea about the distances to the planets, let us look at the time taken by sunlight, traveling at speed much faster than is ever possible for a spacecraft to achieve to reach these planets. You may be aware that the light reaching the Earth left the Sun about 8 minutes ago. It takes 12 minutes for sunlight to reach Mars, 43 minutes to Jupiter, 1 hour and 20 minutes to Saturn, 3 hours to reach Uranus, and 4 hours to Neptune. Traveling at an incredible speed of 300,000 kilometers per second. Traveling at less than 1,000th the speed of light, our spacecraft would take almost a year to reach a nearby planet. Difficult, yes. Missions to the moon and the planets. And yet, there are awe-inspiring stories of lunar and planetary missions, many successful, and some that did not succeed. The first mission to Mercury was the Mariner flyby mission. It returned extreme close-up images of the planet nearest to the Sun. One can easily mistake these to be views of the Moon, as our satellite and the innermost planet are so comparable in size and features. Many detailed studies of Mercury are expected to be achieved from the Messenger spacecraft, launched in August 2004, the first orbital mission for Mercury. A day on Mercury is really long. Mercury spins slowly on its axis, completing one rotation in 59 Earth days, and it revolves around the Sun in 88 days. As a result of these two motions, the Sun takes about 3 Earth months from sunrise to sunset. Temperature rises to as high as 427 degrees Celsius during the day, and the nighttime temperature plunges to 183 degrees below zero. The fact that Mercury has no atmosphere and is very close to the Sun makes it the planet of extreme heat and cold. A Mercurian day might be difficult to define, as the Sun makes a loop in the sky. From some places, the Sun rises, sinks back, and rises again. A double sunrise. This happens because Mercury momentarily speeds up in its path around the Sun as it comes closest to it. This speed exceeds the speed of rotation about its own axis. As a result, the Sun appears to move in a loop in the Mercurian sky. Mercury, the messenger of gods, was also the planet whose observations were to help in providing support to Einstein's general theory of relativity. We talked of elliptical orbits of the planets around the Sun. In such orbits, planets come closest to the Sun at perihelion and the farthest from it at aphelion. From classical theories of gravitation, one would expect these positions in the orbits to be fixed if there was just the Sun and one planet. However, disturbances from other planets could change these positions, or in other words, make the location of the perihelion of a planet precess around the Sun along the orbit. Calculations of possible precession from classical theories of gravitation seemed off from the observations by about 43 seconds of arc per century. A very minute change, but something which was observable. Aha! Einstein's theory of gravitation was the answer. In this theory, the curvature of space-time close to the Sun predicted exactly the amount of precession of the perihelion of Mercury, that Venus, the